Welcome back, everybody. In the previous episode, we've reviewed the design of the addressing logic card. We simulated it in Logic Sim Evolution. We know that the design works. So the next step is to move that design over to the schematic entry of the CAD tool I use to make PCBs. Use EasyEDA. Because one, it's freely available, so you guys can use it at no cost, and also because it's a better integrated suite of tools than how do you call it, KiCad or KiCad, which is a set of different tools, and it's not as well and professionally integrated as EasyEDA. That's the only reason, but most CAD tools would do just fine, if not all of them. So again, that's the schematic entry. There are 5 pages. This control page, there is a counter page here. That's the jump address logic. There is a bus page and an I/O page. So let's go one by one. Most of what you will come across here you've seen before in different shapes or forms, so nothing will be a surprise. And I will go quicker than usual. So as you've seen before, this is just the power supply part. It's identical to the previous boards. There is only one important thing I need to mention. Capacitor C1 was wrong in the previous 2 boards. I have already updated all the files in the repository, so they are corrected by the time you're watching this. But I had used the same capacitor as capacitor C2, and that is incorrect, and the reason is capacitor C2 is on the 5-volt rail, and that's a capacitor with a voltage rating of 6.3 volts. On the 5-volt rail, that's perfect, it's no problem. But this part here, capacitor C1, is on the 12-volt rail, so I can't really use a 6.3 volt rated capacitor there. And I just lazily copied C2 into the C1 position in the previous 2 designs. If you've made the board before, I know of at least one of you who has made the ALU card, it's very easy to replace it. You can just use your soldering iron to heat up the 2 pins of the capacitor, and you pull it out from the other side. Then you can use some solder braid using your soldering iron at say 370 degrees Celsius. You can use some good quality solder braid to clean the holes from solder and reopen them. And then you can buy this capacitor. I give the part number here. They are available at Mauser and everywhere. And it will fit in the same footprint. No problems there. This is a 330 microfarad capacitor rated for 16 volts. And at 12 volts, 330 microfarad will have more or less the same power delivery as the capacitor I was using previously there, which was rated for 6.3 volts. So if you've made any of the 2 previous cards, the ALU card or the rectifier card, please don't forget, get yourself a new capacitor. Frankly, it can be any capacitor from 220 microfarad and up, rated for 16 volts and up. It doesn't need to be this one here specifically, although I recommend this one, but anything above at 16 volts or above, at 220 microfarads or above will do. Keep in mind that the diameter should be 5 millimeters, and look at the other characteristics of this capacitor here that I'm recommending, just to make sure that the footprint will be okay. Although even if the footprint is not the same, you can always bend the legs a little bit. But remember to please do it, because the capacitor you have installed there, which is this one here in the position of C1, that capacitor will not last. Apologies for that. So this is the power supply circuit, identical as before except for this change I just talked about. That's the power LED with the current limiting resistor. Again, just as before, we have the circuitry for the clock and reset push buttons. I'm not going to explain this again. This is basically a debouncing circuit with a little Schmidt-triggered inverter. And just as before, there are two sets of inputs for the control signals. These come from the backplane connector. They are used when the card is inserted in the system and running full speed. And these are the same thing, but now using dip switches to set the control signals. And the dip switches, of course, are used when you are not in system, when there is no shunt on this header and we are basically in standalone mode. Either way, the outputs are here, and well, including these. They are buffered again and then displayed on LED bars. So that's the buffer. This is an array of 1k ohm current limiting resistors, and this is the LED bar. Because there are more than 8 control signals, we need 2 of these sets. The other one is here. And then most of the control signals need to be inverted. That's why we use these inverters. 2 of them don't need to be, and those are the count enables. That's the address register 2 count enable and the address register 1 count enable. They are active high, so they don't need to be enabled. Now the counters page has the 2 address registers, 1 and 2, and the program counter, because as we've seen, all 3 of them are made with 74161 counter registers. There are 4 for each, so this is AR1, this is AR1, this is AR2, and this is the program counter, and they are connected in the same way and for the same reasons as in the simulation. Then there was some space available on this page, so I just put the bypass little capacitors there, 100 nanofarad, one for each IC in the design. And the pins that need to be pulled up, this one here needs to be pulled up. Same thing for this, same thing for this. And then there is another one here, which is the count enable for the program counter, because it should always count, and the count enable is active high, so I pulled it up. So there are 4 pull-ups. I'm using a little resistor of 2.2k ohm in series with VCC. Instead of putting VCC directly on the pin, you can put VCC directly on the pin. The input impedance of these pins is very high, so there will be very low current draw anyway. Normally we use in-series pull-up like this when the pin is not only an input but an I/O. In other words, the pin can be used for the chip to receive some information from the outside, but also for the chip to put out some information. For instance, the 6502 processor has a pin that is an I/O. I believe it's the out pin. You can out the processor from the outside by pulling that pin down, but sometimes the processor puts itself in a halt state or in a wait state, so it pulls its own pin down, and then if you put 5 volts on that pin and the processor tries to pull it down, you have a short circuit. So to avoid that, you have to put a little in-series resistor like this. This is not the case here, so why am I doing this? Well, it's good design practice, and worst case scenario, it serves as a current limiting series resistor in case something goes wrong with the chip, the chances of which are practically 0. But resistors cost nothing and they're very easy to place en route. So just good design, hygiene, and practice. I just put them in there. That's the jump address logic. I call it logic, but it's basically the 2 jump address registers, JAH and JAL, jump address high and jump address low. I'm using a 377 chip for this. They have load enables, which is handy, and they don't really need to be reset because the jump address register It's not a pipeline register. So that's why I'm not using the equivalent chip that has a reset instead of a load enable. I don't need to reset it, but it's handy to have the enable built into the chip. Otherwise, I would have to use some external logic to do the enable. And beyond the two registers, this is just the stuff to visualize things. So all of this circuit here is just to visualize the address register 1. So you have separate buffers for the 16 lines, and then in series 1K ohm resistors for current limitation, and then the two LED matrices. And then the exact same thing to visualize address register 2, and the exact same thing to visualize the program counter. And then, once again, the exact same thing to visualize the contents of the jump register. So this is all pretty trivial. Most of it's trivial stuff. I call this page the bus. Let me try to recollect why. Oh yeah, this is the internal bus lines that come from the backplane connector. These here as well. So this is internal bus high and internal bus low. So these signals all come from the backplane connector, and they are to be used when the board is in system. Otherwise, the contents of the local bus, which are here on this side and here, so local bus high and local bus low, they are either driven by the internal bus signals coming from the backplane, or they are driven by these two dip switches. And the selection is made by enabling one of these two buffers. Whichever one is enabled will drive the local bus, either from the internal bus signals coming from the backplane connector or from the onboard dip switches. And then we want to visualize what is on the local bus. And for that we use, again, separate buffers, in series resistor arrays for current limitation, and two LED bars, because we are talking about 16 bits here. And then there was a little bit of space, so I put the decoupling capacitors there. I think this time I'm using 11 decoupling capacitors. There are more chips on this board, and I didn't really calculate anything. I'm just doing it by feeling, and I think I placed 10, and I thought, oh, I'd like another one over there. So yeah, this is over-engineered, but they cost nothing. And since I'm using a 4-layer board, of which 2 are planes, the power plane and the ground plane, then they don't even make the routing any more difficult, because wherever I put them, there will be the 2 planes underneath. And finally, the last page is the I/O. So these are the backplane connectors. Now there's one thing here that you should notice. Early on I said I wanted the backplane connectors to be such that I could place any card anywhere so without a specific place to connect a specific card. Wherever there is a socket available, you could plug any card in there. Well, that works across the ALU and the register file cards. You can swap them around and they will still work. But for this one, we have a dedicated space, and the reason is there are 2 address buses that need to go out to the motherboard. The PC bus, program counter, and the external address bus. And that's 32 signals, and I counted the available pins on the backplane connectors I chose, and there wouldn't be enough if I would make everything dedicated to only one signal. So I'm reusing here the lines that were used between the register file and the ALU for them to talk to one another around the buses without using the buses. A 32-bit wide direct connection between the register file card and the ALU. These are the pins that were used for that. But that's only needed between those 2 cards. So I decided I'm going to reuse those 32 lines for the external address bus and the external program counter bus to save space, but save pins. But the consequence is that the slot where you can plug the addressing logic card will now be dedicated. There will be a place where it's the only place where we can put this card. It's a trade-off. But I think it's a very reasonable one. And finally, these are the buffers that drive the external address bus. So the external address bus here on the bottom can be driven either from the address register 2 or from the address register 1, which are these signals, these lines here. And which one? Well, that's given by these control signals here. Address register 2 output enable or address register 1 output enable. That will decide which of these two pairs of buffers will be enabled and drive the external address bus. And regarding the program counter bus, only the program counter register can drive that bus, but I still put buffers there to provide some extra oomph to the signal just before it enters the backplane connector, not counting on the register chips to drive the line all the way across the backplane into another board. I decided to put these buffers there, and it has an extra reason. I should be able to tri-state these buffers based on this control signal, the program counter output enable, and that's crucial if I want to enable Talos to be DMA capable, to allow for direct memory access, because if the I/O controller wants to access the instruction memory to load the new application, then these two buffers here will be tri-stated, releasing the program counter bus for the I/O controller. And then here some more bypass capacitors where I had space. And that's basically it. That's it for the schematic entry. It's pretty simple. Let's look at the board now. Let me open the board file. Come on. There we go. That's the board. As I mentioned to you, it has 4 layers, and the reason is it was becoming very tricky to route the power rail and the ground rail without using planes, and it was possible. It certainly is possible, but not with all the sandbagging and that I wanted to add. So I decided to add 2 inner layers. Inner 1 is a ground plane, and inner 2 is a VCC plane. And then all the actual signal lines are on the top layer or the bottom layer. Everything is routed there. So everything's still visible. You can still completely reverse engineer the board just by looking at it. Now, for us to see better, let's hide the copper areas so we can see the signals. So the preferential direction rule of thumb has been applied here. So you can obviously see that the top layer in red, the preferential direction is vertical. That's the one that dominates. And if we go to the bottom layer in blue, then the preferential direction is horizontal. That's basically it. I did have to make some compromises here. I mentioned to you before that it's better to route a signal as a snake from one point to the next, and then from that to the next, and then from there to the other one, as opposed to having branches. It's better that it be a snake than it be a crab, because it reduces reflections. But I couldn't do everything as a snake. For instance, you can see this signal here. There is one branch. If you go to the next one, there are 2 branches on this net. The next one branch, 2 branches, 1 branch. So you get the picture. There are 2 branches on this one. So there are branches, usually only 1. I think everywhere there's maximum 1 branch. And although I don't like it, for the speed this will run, it should be okay. And I'm being very careful about using always these transfer vias and return path vias, and in this case they work as both, because I'm using planes now, so when I go from the top layer in red to the bottom layer in blue, I'm changing the reference plane from ground to VCC, so we need a transfer via to sort of keep the field fringes tight as we move from one reference plane to the other. And they also provide a return path for the return current to ground. So I'm very assiduously using these return path vias. Here I didn't, and I just noticed it now. I completely forgot return path vias here. What a bloody blunder. But I'm not going to make this again. The board works. Oh, what a pity. I probably didn't see it because I had the copper areas on, and it's difficult to see through all the copper. So I probably didn't notice for that reason. But it's okay. These are VCC vias, right? Yeah, they will not work as return path vias, but they will work. They will work as transfer vias. That's not a problem. So this is not too bad. And there is a big ground pin right here. So the return path for these signals will probably spread and come to this ground pin and will not spread any further. It will end here. And it's a capacitor, which is even better. It's more helpful. It will provide the electrons for the return path. So this should be okay. But it's an error. There is no... I didn't avoid putting the return path vias here for any reason, for any good reason at all. I just forgot. And I'm not going to change this because I don't want to put online Gerber files for a board that isn't exactly the board I made and tested myself. And I'm not going to make another board and test myself just because of this missing return path vias, especially because we have the transfer vias there and we have a big ground pin very close by, which will work as a return path via, so to say. So this is okay. And there isn't much more to comment except some electrical details. I am using these two resistor networks here. They are 33 ohm. I'm using them in series after we select whether the local bus here on top is connected to the internal bus via the backplane, which comes from here, or from the dip switches, which are there. So after the selection is done, you can see here the blue lines of the dip switches go into the inputs or the low side of these resistor networks. So does the internal bus signals from the backplane. So after the resistor networks, there has already been a selection. Where do the bus signals come from the backplane or from the dip switches? And therefore, afterwards, they go through the 33 ohm resistor networks, which are there to absorb reflections after the selection is made. So when the signals go here along these lines, and you see there are branches, there are always branches, you get reflections. And because I didn't want to eliminate all the branches and make the board design very difficult to understand, I wanted it to be clean and didactical. Instead of removing all the branches and make everything a snake, I put the 33 ohm resistor networks there to absorb some of the reflections. Branches will not necessarily cause reflections. They will just worsen the reflections in the sense that each branch will have a certain resonant frequency different from the others. So there will be more reflections, each one corresponding to the resonant frequencies of each branch. But hopefully these two resistor networks here will absorb the brunt of it. And there won't be much of a big deal with that. Here on top are the circuits to visualize the contents of the internal bus. So internal bus high and low, you visualize in these two LED bars, and then you visualize AR2 here, AR1 here, PC there, and the jump address high and the jump address low you visualize here. And then these 4 chips here, plus these 4 chips there, and these 4 chips here. These are the 3 counters, AR1, AR2, and the program counter. They are all in these chips. These are the dip switches to set the contents of the local bus internally. These are the jump address registers, JA high and JA low. And this stuff here is there is a buffer here to boost the internal bus signals coming from the backplane and allow them to be selected with respect to the dip switches, which have their own buffers as well. Then these are the output buffers for the program counter, AR2 and AR1. And those lines go to the same pins that in the ALU and register file cards were used for the direct connection between the two, so that the ALU could receive the contents of A high, A low, B high and B low directly from the register file card bypassing the buses. Here, the same pins are reused for the two 16-bit address lines, the external address bus and the PC bus. And why there are 6 buffers then instead of 2? Because the external address bus can be driven either from AR1 or from AR2. So we need to make that selection here. And the program counter is driven only by the program counter register, which is this one here, but it's visualized there. But I wanted to boost the signal anyway before sending it across the backplane connector. That's the power supply part, which is in here. C1, the capacitor that if you've made the previous cards, you should change, is this one here. It's right next to the switch, to the power switch, and right next to one of the backplane connectors. This is the one that is now 33 microfarad at 16 volts instead of 470 microfarad at 6.3 volts. This is a 12 volt line, so that will not work. This is basically it. We can visualize it in 3D, although I will show you in a moment what the board looks like, and we will test it together. I already tested it, but I'll test it again together with you. But before we do that, let me just quickly show you the 3D model, which is incomplete because I don't bother loading all the 3D models of each component on the board. That's what it looks like. All right, let's now have a look at the board and test it again. And here's the board in all its glory. 4 layers, everything fit in. You can see the new C1 capacitor there on the side. I'm pointing at it now. The one I'm using here is bigger than the one I'm specifying now in the repository. It's just because I had a bunch of them lying around, so I muscled one in there, but you should use the one I recommend in the repository. Lots of chips, lots of lines on this board, both front and the back side. You can see the little rubber feet I put in there so the pins don't scratch my anti-static mat where I'm going to rest the board in a moment. We are ready to test, but before we test it, just wanted to give you a sort of a set of close-ups of the board. You can see this oversized capacitor I muscled in there. All my boards have this oversized capacitor now. And that's a close-up sort of glamour shot of the board, so you see the details as well. It may help as a reference if you're assembling your own board. I will put lots of photos in the repository as well. Make sure that you have good references. I tried to, when possible, put some copper fill in between critical lines, and then I stitched it carefully, made sure that that metal in between never floats. You can see that area in the center where the control signals come in and the push buttons, backplane connectors. I'm quite happy with this board, even though it was the most difficult to design of all 3 so far because of the sheer amount of signals. And finally, zooming in on the silkscreen markings, identifying the board. So let's go ahead and test it now. All right, let's test the board. I have already connected the 12 volt DC center positive power supply. I just need to turn it on. Let's turn it on now. It is on. There is only one control signal that is active. Well, it's high, and that's reset, but reset is active low, so it's normal to see this one LED shining. If I press reset, it will go low and active, and then it disappears. When I release it, it comes back. So that's normal. Let's do a few tests. The first thing we can do, the program counter is here. Let's see if it will count before we set any control bit whatsoever, because it should always count. So if I press clock, it counts, you see? So that's working as it should. It is counting. So now let's set, it's in standalone mode. It will be only in system mode if I place this shunt on this pin header here, but right now it's in standalone mode. So let's set the local bus, which is the local segment of the internal bus. Let's drive it with a low nibble high on the high byte, and let's do a high nibble high on the low byte. So let's now see if the program counter, what happened to the program counter? Oh, I probably touched something here. So let's count a little bit again on the program counter. Okay, let's leave it there. So let us now load the contents on the bus on the jump address registers, and they are visualized here. The registers are these two chips, but they are visualized here. Let me get my little device to see better. So okay, jump address high, load enable, and jump address low, load enable. So if I press clock now, these two values should go into the jump address register, and there they are. So now I would disable the load of the jump address register, and I will enable the program counter load. So program counter load enable is now active. So when I press clock, this value should go into the program counter, overruling the count I already have there. And there you go, it goes there. If I press clock again, nothing would change because I still have program counter load enable. But if I disable the load on the program counter, now the value will stay there, but when I press clock, it will continue to count from where it is now. And indeed, that's what happens. There we go. See, it even counted across the 2 bytes. So that's a good test. Now let's change the dip switches here. Let's put some other values. Let's say, now I'll keep the 2 bits on the extremes on. So the 2 sides. And for this one, I have to do something else. I put 2 bits in the middle off, and the more bits on the extremes are on, just so we have a different value than this. So let's load this on both address registers. There will be no instruction that will load both address registers at the same time, because they're supposed to be different indices, so I cannot imagine a situation where you want to preload them with the same value. But the hardware allows for it. So to test the hardware, we do it. So address register 1 load enable. Where is it? Address register 1 load enable. There it is. And address register 2 load enable. If I press clock now, then these 2 values go here and here. There they are. So I'll now disable the load, and I will enable the count. First I will enable the count of AR1, and we count only on AR1. Where is it? AR1 count enable. Here won't count enable. So if I press clock now, this will count and this one will stay where it is, and the PC will count as well. There we go. So that's working fine as well. So this is ahead of this. If I now enable the other one to count along as well, address register to count enable. Now both will count, but they will remain different because the starting points are different now. Okay, clock. Yeah, both are counting now. The PC is counting, everybody is counting now, as it should. So yeah, this is working fine. We can test the output enables with a multimeter. I did test it and I can tell you it's working, but it's not going to be interesting to show it to you because I just put the multimeter here to see when the pins float and when they are being driven, and that's correct. What we can do is put this shunt across this header, and then the board will be in standalone mode, which means that the internal bus will not be driven by the dip switches. It will be driven from the backplane connector, which is not connected, so the bus will float. Let's see. And indeed it floats. Even the control signals, which now come from the outside, are floating. If I put my hands on top, you see? If I run my hands close and the pins of the backplane connector pick up the disturbances that my hand, the presence of my hand provokes on the electromagnetic fields around here, and you see them, you see that disturbance on the LEDs, even in the control signals, which come from around here. Yeah. But if I disconnect it, then it's again driven by the dip switches. The bus is driven by these dip switches, and the control lines driven by these two dip switches. So, conclusion, it's working fine. We can go to the next board, which is the control card, and it's well, it's pretty simple in terms of what people are doing today. But in the context of this project, it's the most complex card and should be a lot of fun. But I'll not be able to do it in the next couple of days. It will take a couple of weeks now until I can get back to that. Till then, take care, and I'll see you next time.